Okay, well, it's 3:05 here. I think we should get started. I am very excited to have David Pan here. I've gotten to know him, working with him on some projects related to circuit design and machine learning. He is arguably the world's expert in that topic. He's a professor of electrical and computer engineering at UT, and he's one of the members of our Institute for Foundations of Machine Learning. We have a project going about with circuit design and its relationship to machine learning. And he's also one of the leaders of a new AI institute on optimization that is also going to feature similar topics that I'm sure he'll get into. And so I'm excited to have him here to tell us about this relationship between these two really fundamental problems in computer science and electrical engineering. So take it away, David. Thanks for being here.
Okay, thanks very much, Adam. So you can hear me okay? Good?
Yes.
All right, great. So yeah, in this talk, I will talk about closing the virtuous cycle of AI for IC and IC for AI. As we all know, AI has been really a hot topic in the last 5 to 10 years. And I think the reason behind is this, what I call ABC, right? You definitely have a lot of new algorithms from, convolution neural network, RNN, GAN, all kinds of new, architecture algorithms. And on the other hand, there's a huge amount of data, right? And being collected so that, we can do training on those sophisticated algorithms. But meanwhile, right, so you do need to have a humongous amount of computing power needed to train those complicated algorithms and high volume of data. So my research is a really intersection with this AI and chip aspect. When we talk about chips, right, of course, you have conventional CPU, general purpose computing, and then also, GPU. For example, NVIDIA is doing so well, and its market cap is, I think probably 3 times of Intel now. And then there's a dedicated ASICs and also field FPGA companies, which are targeting those kind of AI accelerations. So since my research is kind of linking this AI and more like a hardware and software aspects, let me just give you a sense of how modern IC design kind of and manufacturing looks like. Right? So for example, this is the NVIDIA system on chip. It's actually already there for a couple of years. As you can see, it has 9 billion transistors in a very advanced technology node, like a 7 nanometer or stuff like that, right? And it takes 8,000 engineer year to really develop such a complicated autonomous driving chip. And design such kind of chip is non-trivial at all. You can imagine, right? You need a very, disciplined design kind of flow. For example, divide and conquer. But even within each of these kind of sub blocks, right? And you may need to take like days to do all this iteration to reach all the so-called power performance area target, right? And you probably also heard that there's some startup company like Cerebras, the entire wafer is an AI chip, okay? So when you are talking about this is already billions of transistors, right? This kind of wafer scale chip, it's not really a chip, right? So many chips there with trillions of transistors. So you can imagine, wow, it's like, the design complexity and all this, manufacturability challenges and all this is really huge. And what is more, right? When people usually finish the chip design, right? Usually, if you are not from a EE background, but in general, once you finish the chip design, people call it the tap out. So essentially, you have different mask layers to describe the geometry of each transistors and wiring and at the different layers and connections, etc. Right? But when we are in such an advanced chip like a manufacturing process, right? What you see at the design is not necessarily what you get at the fabs. Because these features are so small and you use like optical lithography to try to print them. And there's always light scattering and so on and so forth, right? So you have to use a very sophisticated computational lithography to make it, what you print on wafer kind of close to what you are going to, you really design, right? Again, right, as I just mentioned, right, such kind of design and manufacturing is really, really complicated. It's unbelievable. So usually, right, so you have a kind of top-down approach, at the higher level, maybe you have more CS background people, try to write some high-level description language, and then, or hardware description language, you specify the designs and then architecture and then functional logic design. And then you kind of go, to more physics and engineering, electrical engineering, say, hey, what is the logics? And then how do you do physical design, the layout? And then, ultimately, what is the mask synthesis, verification, and so on and so forth. Ultimately, you are going to fabricate, and then you package and testing, right? I mean, here is already a simplified view. Even within physical design, there are many, many steps, such as like a big macro floor planning. Then how do you place all these millions of, billions of transistors, right? And then how do you do routing, right? So, and so on and so forth. And then in the mask stage, you have to verify that what you are going to fabricate can really be fabricated. And so otherwise, if the fabricated chip doesn't work, you have to go back and check, hey, which step goes wrong? And then you may have to go back and this so-called iteration. So if you have so many of these iterations, then remember each fabrication step, you easily talk about millions or even tens of millions of dollars, right? So that's why you cannot afford to screw up, right? So that's why design and manufacturing is so complicated, and we are also, the design of all these chips has very, stringent performance, power, area, all kinds of, requirements, manufacturability, yield, reliability, security, or you name, right? So with all this, of course, nowadays, right, the design cost, you probably heard about Moore's law, right? Moore's law essentially is saying that, hey, as your kind of design, number of transistors kind of doubling every 18 months and so on and so forth, right? However, there's some corollary, which, people don't usually talk about, but, basically the design cost also increased like Moore's law. So that is certainly, not very affordable. That's why nowadays, right, not so many companies can afford to design state-of-the-art chip with such kind of billion transistors, right? So that's why 3 years ago, DARPA started this ERI initiative, Electronics Resurgence Initiative, and they're investing $1.5 billion on this. And among this, there's a Silicon kind of compiler 2.0 program, which, their goal is to say, hey, can we have a no human in the loop 24-hour turnaround time kind of this kind of DARPA grand challenge and mission, right? So, well, of course, one of the motivation behind is that, hey, because, there are a lot of AI nowadays, right? Can we try to use AI to help design state-of-the-art chips, right? And reducing all this cost and so on and so forth, right? So the answer is certainly yes. And my talk today will try to basically motivate this and close what I call virtuous cycles between AI and IC. So on one hand, what do I mean AI for IC, right? So the goal is to leverage AI hardware as well as software, right, to enable agile and intelligent IC designs. And meanwhile, so everyone heard about the Moore's law, right? So Moore's law not only is just number of transistors, but also, what kind of equivalent performance, power, and all this nice, good stuff, Moore's law can provide. And on the other hand, right, so when I say IC for AI, so you probably heard a lot of customized IC and accelerators for AIs, right? Because AI does need a tremendous amount of computational power, right? So how can we design energy efficient and hardware aware machine learnings such that your AI can run very efficiently, very fast, right? So that's why there's this kind of, virtuous cycle between them. So that's actually interesting. Everyone probably heard about Moore's law, right? This is one of the most amazing law. It has been true for the last 50 years, which, that's, your number of transistors kind of doubled every other year also, right? So very interesting, in the last 10 years or so, right, the number of machine learning papers, right? So of course, those are mostly software related papers, also upward, kind of Moore's law, or even bit Moore's law a little bit, right? Anyway, what is my point here, right? My point here is that, hey, if we have these two, one is hardware kind of Moore's law, another is more software Moore's law, work together, it will be tremendous, right? Whether you will get Moore's laws, exponential to exponential, exponential times exponential, whatever, right? I think that will be really, really amazing. So what I will do in the next maybe 40 minutes or so, I will give some case studies to show what we can do for AI for IC and also IC for AI. I know that this audience is a very broad audience, so I'll try to stay at higher level so that you can get the key ideas. But if you want to dive into details, feel free to reach out to me, and we'll be more than happy to answer any questions after that. So the first case study to basically leverage AI for IC design or design automation is this new placement engine that I call DreamPlace. It essentially leverages deep learning toolkit for GPU acceleration for modern VLSI placement. So we have also made this open sourced, and we actually had the honor that this work has won Best Paper Award at a Design Automation Conference 2 years ago, and also most recently we just got the IEEE transaction on CAD Best Paper Award, right? So it actually has this technique has already been widely used by industry, and including NVIDIA, Google, etc. So first, what is placement? Placement is actually a very classical EDA problem. Essentially, think about it, right? When you have a chip, right? You have big macros. You also have these little dots. These dots are like you're talking about millions or tens of millions of standard cells. Basically, these cells, they all have connections, right? Because this, for example, NAND gate need to drive another inverter, which drive another flip-flop, and also ultimately you have to place them in this two-dimensional chip, basically, image, and without overlapping, right? But because they have interconnections among themselves, and it is to get wire length and the timing and all this correct, right? Because without place the chip on this 2D image, you don't know how long your wire is, and when you are scaling to nanometer designs, those kind of interconnect is the first order, right? When you are talking about timing and power performance, right? And this is actually a very classical topic, and it's MP hard. So because of this, the placement problem has been studied more than 50 years, right? Even before ever since people have designed the chips, right? You have to do placement, right? So this is a complicated slides. I won't show you details, but basically you get a sense, every year there are probably a bunch of papers people have already published for placement. Even get 1%, is like pretty impressive, right? So you have like early stage, people use partitioning, and later on they use multi-level partitioning. There's a simulated annealing. Then recently, people have been using more analytical techniques, essentially formulated into some kind of, for example, nonlinear optimization problems, and so on and so forth. So currently, the academic state of the art is more like a formulated placement problem into some kind of nonlinear optimization problem, okay? So what is a state of the art nonlinear placement optimization kind of formulation looks like? So essentially, to put it in a very simple view, you want to minimize the total wire length. X, Y are like cell locations, right? You want to minimize the total wire length if you have some net connections, right? And meanwhile, if you just want to minimize wire length, it's not very interesting. You do want to spread your cells, because otherwise all the, this standard cell, on top of each other, and then, wire lengths are zero, but that's not interesting, right? So because of this, usually we will, make this constraint optimization into some kind of unconstrained optimization with this kind of density as a penalty function. If your density is too high in any location, I'll try to penalize it with some kind of Lagrangian relaxation factors, right? But you can imagine to develop a state-of-the-art placement engine, it takes tremendous amount of effort. And also the runtime of this, when you're dealing with millions or tens of millions, placeable objects is very, very high. So then, as a researcher, you may come back and say, hey, what is our dream placement engine should look like, right? we definitely want to have the best quality results, really, really fast, and with low development overhead, and also very extensible to get, if you want to get new algorithms, new acceleration techniques, you would like to say, hey, I can easily just, slightly change my, core placement engine. I can directly, very quickly test those algorithms, right? So, well, want to dream big, right? So one thing actually motivation for us is that we noticed that, with all this recent deep learning, advancement, right? The hardware, for example, the GPU or all kinds of AI accelerators, has been growing in terms of their performance significantly faster than the conventional CPU, right? And there's, of course, all kinds of even dedicated AI accelerators, even, can get a much better, PPA, those gigaflops, etc. Right? Meanwhile, there's a huge, a software community. People have been contributing to deep learning softwares. They also have made it open source. For example, Google has Google has TensorFlow, and Facebook has this PyTorch, right? So these are pretty popular ones, among others, right? So this actually, because so many developers have been trying to make those, better, right? So we actually, this algorithm, these toolkits have been highly optimized. And our dream place strategy is to propose a novel analogy between, basically a classical nonlinear placement optimization with the neural network training problem. Okay, I'll show you soon. So by doing this, instead of developing a new placement from scratch, we can actually greatly leverage deep learning hardware as well as software, so that we can get the state-of-the-art result, but meanwhile we can allow very, very high parallelisms and acceleration while getting state-of-the-art results. All right. So let me show you the analogy between neural network training and the placement problem. As we know, right, so when we are doing neural network training, so suppose you have certain data instance, you have a label, right? So you go through a forward propagation, you can compute the error function with certain weight, right? And then you compare it with this label, right? Then you do back propagation. And when you do back propagation, forward propagation many times, and hopefully at the end, you already train your weight, which will minimize your error function. But to avoid overfitting, you can introduce some regularization factors, right? If you now look at your wire length minimization problem for the placement, meanwhile you want to spread your cells to be more or less even among the chip image, right? So we actually can cast this, have an analogy like what is our data, right? Our input is your interconnection in the connections, right? And your target, you want to minimize wire length. And then, so it turns out that if you want to minimize wire length, the error function is the wire length, okay? If you set your target to be 0. And then, you can do a forward propagation to compute wire length. And then you can do backward propagation. Then the weight here essentially is your XY location that you want to determine what's the, cell locations, right? Anyway, I won't go into details, but, as you can see, there's a beautiful analogy between solving this classical placement problem and the neural network training problem. One thing I like to mention is that we don't really need any training data. Essentially, we are using the infrastructure that modern deep learning, like a community, including hardware and software people have been developing. We are then porting this to solve these hard problems, right? And of course, that means, when we're developing our new dream place architecture, right? So we can actually leverage all these nonlinear optimizers, automatic gradient computation, etc., from the mature and highly optimized deep learning toolkits. And meanwhile, we of course need to customize our placement API. And we also, of course, need to customize the wire length computation engine and the density with all kinds of optimization and acceleration schemes, right? But due to time limit, right, I won't go into details here. But anyway, so we actually developed this engine, and we also try to match the previous academic state-of-the-art placer, which was published at the IEEE Transaction on CAD in 2018. So we replace this placer, on many core CPU. Okay, but for our dream place, we only have one CPU pretty much to read the design. But then the core placement engine is run on one NVIDIA. Okay, Tesla, GPU. And because we try to match the two algorithms, because anytime you have these analytical placers, there are a lot of parameters you have to tune, right? But we try to match this to get the same quality of results. However, and with dream place, we can be 30 to 40x faster than the previous academic state of the art. And for the largest benchmark that we got from NVIDIA, which we collaborated with them, this previous academic placer just crashed, right? And we can just finish it in 5 minutes, right? If they don't crash, it will easily take them several hours. So that's really actually very nice. So remember previously when we try to think big and dream big, right? So remember, we want to have the best quality. We want to have the really fast. We have low development effort. It turns out that previously, to develop a state-of-the-art placer easily take a year, but with our dream place framework, only a couple of months. And then we also found that it can be very extensible to new algorithms and new acceleration schemes and so on and so forth. So essentially, our dreams come true, right? So we can even dream bigger. So it turns out that, as I mentioned, right, we can use new solvers, right? Because in the key machine learning community, that's why I'm very excited to collaborate with Professor Adam Clevens and his new IFMR Institute, as well as Tilos Institute, who has a lot of really foundational machine learning people, right? So, I mean, there's, of course, a stochastic gradient, add-on, etc., right? Let's say, hey, some days there's a really nice new solver comes out. We can easily plug them in. And we can also adapt to consider different objectives, right? Remember, for placement is really fundamental. And in chip design, you care about timing, you care about power, you care about routability and all this, right? No problem, right? We can just add them. And suppose also in the new acceleration schemes people develop, right? When you have multiple GPU, distributed computing or cloud computing or mixed precision training, and so on and so forth. No problem, right? We can also accommodate that. And recently, actually, Google Brain published a paper in Nature that showed that using reinforcement learning, that can actually help macro placement, which is used to be a very heavily manual step chip designers do, right? So they show the superhuman results, right? Actually, we collaborated with their team, and we use DreamPlace to replace their original placement engine. We found much better results, right? Anyway, there are also other CAD problems. We can actually adapt this kind of framework. So that's why I think this is we can definitely dream bigger. All right, so far I have shown you the first case study of DreamPlace, right? That's mostly for digital IC. Usually when people talk about IC design, there's a digital IC which is mostly large scale, but there's also analog IC. Analog IC typically is, in terms of number of transistors, is not so many, but the design is really hard, and there are so many design constraints. So I'm actually leading the DARPA project on this Magical, and we also have made it open source, and we even have chip tapped out using Magical. Let me just quickly show you the key idea, right? Analog IC is very important. For example, analog digital converters or digital to analog converters, because when you are dealing with outside world, whether it's a 5G, 6G, or biomedical systems, so all these real world things will be analog signals, right? So you do need to have analog. Once you kind of analog to digital converter to digital signals, then you can use all these large scale digital to do all the computations, right? But the design automation for analog IC is not very successful and used much in practice, like digital. The reason is because there are many reasons. There are so many constraints and so on and so forth, right? what we have been doing in Magical is to develop a fully automated analog layout systems, leveraging human and machine intelligence. We have published a lot of papers on this, but let me give you a high-level picture, right? So essentially, the Magical input is some kind of netlist. I mean, in our world, right, you will write it in certain kind of spice netlist to describe the circuit, behavior. And then, you want to generate a certain output, which is ready to be fabricated, for example, at TSMC or any of the foundries, right? But that needs to be, all kinds of design rule clean, and also, the logic has to work, right? But, the key components of Magical, including, device generation and layout constraint extraction, and also placement and routing. I won't go into details, but basically, inside this Magical engine, right, we have used a bunch of machine learning, like pattern matching or some deep learning, but we also used analytical techniques and also some heuristic like A* search for routing, right, which people widely use in the routing community. So we also handle not only very small block, right? Let's say you have a very complicated like ADC designs. It has some blocks, but meanwhile you need to put this block together to put it into a systems, right? So usually those kind of designs will be described in a pretty hierarchical manner, but no problem, right? Our Magical can handle those hierarchical manner, and we can automatically do block level synthesis. And meanwhile, at the top level, we can integrate that. And as I already showed previously, right, basically we have those layout constraint extraction. We can automatically extract all kinds of symmetrical constraints. We can do all this, because for analog designs, right, you need to kind of, for example, these two blocks need to be symmetric with certain y-axis, right? Stuff like that. They're like, that's why, analog designs, oftentimes in the past, people are thinking, wow, it's like an art, right? But, when you're doing it like an art, it takes the human designers a tremendous amount of time, right? Weeks and months to do those, right? But with Magical, right, we can do it to push a button and really no human in the loop, right? So we not only have these tools open sourced, but we also tried it in some very advanced analog IC design. I won't go into details, but it's some delta sigma modulator and this is schematic. And we actually have the chip tap out at TSMC in a 40 nanometer. And then we actually compared it with some previous state-of-the-art designs. And in particular, we compared with the previous manual design. This is actually done by a PhD student at UT Austin, of Professor Nansuns, who was my collaborator of this project. And we are using this is a fully automated approach. This is a really manual approach. And as you can see, the layout of the full manual approach and our automatic approach looks pretty similar. So that's actually great, right? And we also compared all kinds of, I know this is kind of very busy, like a matrix, right? But usually, right, for analog designs, they care about a lot of differences, from like the power area, like bandwidth and some kind of, figure of merit, and they care about a lot of things, right? So we actually can do head-to-head comparison, and we found that actually we sometimes even get better results than the manual results, and sometimes a little bit worse, but in general, at least comparable. But in terms of time, right, a manual designer to do this, it takes easily a couple of months or more, right? But for us, actually, the entire thing, it only takes a minute, right? So that's actually very, very significant, because that means, we can also change the parameters because it's the automation, right? So we can easily change some parameters to, run many iterations, right? But for them, for human designer, it's just impossible to do that many different iterations, right? All right, so now let me also show you another case study, which is related with something called design and technology co-optimization. So usually, when we are doing design, right, so ultimately it has to be fabricated, right, as I just showed at the beginning, right? And as I already mentioned, lithography is the dominant manufacturing process. But the problem is that, as I already showed you, right, so when you're dealing with lithography, you have certain masks, and then you shed the light and try to print them, right? So it's not really, what you see, is what you will get, right? But this kind of simulation is very, very nasty, For example, right, using some really, there's a lot of, how do I say, physics, chemistry, photolithography, and etching, a lot of stuff involved. And very detailed simulations, even for 2 micron by 2 micron area, which is really small. 1 micron is 10 to the order, -6, right, meter. And, your chip could be millimeter or centimeter, right? That means, it's 1,000 times bigger than this, right? So that means millions of minutes to do this full chip this kind of really detailed simulations, right? So it's really, really, so that's why what we are trying to do is like, hey, can we, instead of doing this kind of very detailed simulations, we will just do direct inference, okay? So that's why we proposed some framework using GAN to do this kind of direct inference and to directly get this kind of printed image. And once we do that, actually, we can bridge the design and manufacturing gap. And this actually is one of the really, really important issues because, think about it, right? Those fabs cost billions of dollars, right? So your design, if you design something which, the fab cannot fabricate, that's not good, right? So there's a really very important handshaking between design and manufacturing. So what we have been inspired, to do this kind of research is really inspired by GAN. I'm sure, a lot of audience in this audience probably already know GAN. Stands for Generative Adversary Network. It has 2 neural networks, basically, compete with each other. One is generator, another is discriminator. And then it's like, for example, your generator can generate a fake US dollar, and that discriminator will say, nah, that's fake. And then you go back and try to improve it. But anyway, there's also another way to do GAN. It's called conditional game, which can take an image from one domain and then translate into another. Right? I won't go into details, but this is a really, really widely used technique, in the computer vision communities, right? But what we are trying to do here is like, hey, you give me a certain mask, and then, instead of doing very, very expensive lithography simulations to get some printed image of the features that you care about, right? What we are going to do is, hey, can we bypass it and just use direct image translation and then get the printed image of some features, critical features that you care about, right? Again, I won't go into details, but you can imagine, wow, this actually sounds like a very good GAN problem, right? So that's why we proposed to solve this using GAN, and we collected a lot of samples to train our GAN network. And I won't go into details, but GAN has generators and the discriminators and stuff like that. And the good news is that we found, interesting, right? We found that indeed it works pretty well. Compared with very rigorous simulations, right? Our GAN can be thousands of times faster, but meanwhile, in terms of the error, you're talking about, pretty acceptable error, even when we consider consult with industry, right? So you can imagine with these kind of things, you can really, open the door for future kind of design and technology co-optimizations, right? How do you make a, more, printable designs while trying to push power, performance area, and yield, and so on and so forth. Right? Again, right, that's actually a very open research topic. All right, now let me, move on and talk about another topic that's kind of try to close the loop towards the IC for AI aspect. So we already know that modern designs has tremendous amount of the customized AI accelerators. Nowadays all the phones have neural processing units, right? And Google has the TPU. I think it's quite a few generations now, right? And so on and so forth, right? But all this, your goal is to have those AI accelerators dedicated, they are really fast. Instead of using general CPU to do those, machine learning tasks, you use these neural processing units, right? And but these are all based on, the conventional transistors, which are transistors, right? And electronics, right? So what, we are trying to work on, of course, academic, the industry has been, has huge efforts on this, right? What I will talk about today is on some photonic AI chip, in the sense that basically by playing with light, you can also do some using optics to do some photonic kind of integrated photonics to do this kind of AI accelerations, right? So it turns out that this was one of some early work is done by MIT in 2017. They published the Nature photonics paper, and after that, there are already a number of startups from MIT. I think these two are from MIT. Meanwhile, from some other companies, and try to build AI accelerators using photonics and optics. So let me just show you the key idea, right? So I think one of the key operations, when we need to do AI accelerations is to compute the matrix vector multiplications or matrix multiplications, right? So you can think about, okay, if I can kind of configure my optical device or integrated the photonic device such that they can implement some kind of weight matrix when your light comes in and then your light comes out. So the light comes out, let's say, will be, once your light shines in and then goes through this configured optical device, you will let the physics, or optics do the matrix multiplication for you. And then you can measure the light intensity, and the intensity here is basically the matrix vector multiplication. All right. So that's the main idea there. So essentially, as you can see, it's some kind of analog computing. It's not digital computing. You directly use this device to do the computing for you. Of course, you need to have some detection, and they show that you can really detect them. And the nice thing is that once you configure this optical device, it doesn't consume power at all to do matrix multiplication. Okay, because light comes in, light comes out. No power is consumed, or very little power is consumed, right? So of course, when you tune them, they take some power. But if you are using it for inference, it's already trained, right? So you already configure it properly, right? However, there's some problem. What's the problem, right? The main problem is that the area of this kind of device, this, for example, here they're using some kind of MZI array. Don't worry about the details of physics, but you can think about in electronics, the basic building block is transistors, right? Nowadays you are talking about 7 nanometer or whatever. You are talking about nanometer scale. But for the optics, the MZI array or those micro disk or micro ring, you are easily talking about micro, 1,000 times or more, in terms of dimension. Okay, so that's why, although this consumes very little power and very very fast, because you are really computing light of speed, right? Speed of the light, but they are very bulky, so you cannot afford to run very big matrix, right? And very big network like this. So that's why you need to have hardware, software co-design such that you can have more like. Let me just show you. Right, I know this is a very, very busy slide. It just shows you there are many, many efforts on this area, because this is a very, very fascinating and very, how do I say, interdisciplinary area. And people in the physics, people in EE, people in computer science, they can all work on this on different angles, to come up with new network. Early stage, this is stuff like that. So, but basically, today I will just mainly focus on several aspects, 2 aspects. One is area efficiency, right? You do want to basically have a new architecture, and which use the smallest number of devices. And also, for those optical devices, they are actually, because they are less mature compared with the electronics, right? So the robustness, you need to consider this while you are doing training. And also there are all kinds of learnability issues, right? But what is my key message here before I jump next is that with this, we do need to have a lot of hardware and software co-design, right? So one of the case studies that I would like to talk about is this so-called FFT-based optical neural network. So what's the key idea, right? So when MIT folks, try to build their kind of, this array structures, they start from some MZI. And they assume that that MZI can handle very general matrix multiplication, all right? However, we found that, okay, we can actually build a more specific kind of architecture based on so-called FFT, right? Don't worry about the details. It's some kind of, we will build the architecture based on those more like primitive couplers or phase shifters and so on and so forth, right? And the key idea is like by doing this, we can use much less area. But there's a little bit of con here is that this kind of architecture can only handle circular matrix multiplication. Okay, so it's not very, very general. However, there's also people in the very hardcore machine learning community which have shown that, hey, when we do kind of training, if you just pick your matrix as some kind of weight matrix as a circular matrix, they have also shown to have good kind of expressiveness. So hey, if that's the case, that's great. We can get much smaller area and less latency and better energy efficiency, right? So again, due to the time limit, I won't show how detailed we do it, but we can show that compared with the original, MIT paper, our area can be like 3x, less, and we got the same accuracy, and we have also, also almost a factor of 10 better energy efficiency and less latency, right? So we also actually, not only we have done this theoretical work, which actually got the best paper award 2 years ago at the ASP DAC, but we actually tapped out a chip, right? It turns out that tapping out those kind of optical neural network chip is non-trivial, because it's not like CMOS, so many there's a mature fabs, right? So the optical chip, right? Not so many mature fabs yet. So we went to Singapore and to tap out our chip. And once even when we have the chip comes back, to really measure it and all this, it takes us, more than a year or so, right, to really get it measured. And so this is our chip that comes back. But the good news is that we found that it really works, and we can get a really nice kind of experimental demonstration. So yeah. So compared with the original one, right, we can get much smaller footprint and lower latency. Right? So we also extended this kind of framework to handle from the general, FFT, fixed FFT structure to more general frequency domain transforms. Again, don't worry about the details. I would say, right, the key idea here is like previously, right. So your like architecture, you have like a FFT and inverse FFT, right? But now we have a certain kind of transform, but then we'll have a reverse transform, which is not necessarily the inverse one, but kind of, we make it trainable. And by doing all this again, right, so we can get even better area and also much less power, right? So don't worry about the details. And so essentially, we can save the power even more. So another thing, I think this is a very, let me just quickly show you a core idea, right? So another thing is that we can play with the device, right? One of the widely used device, that's why, by the way, this work, I'm in close collaboration with Professor Ray Chen. He's running like a DoD Murray Center, Multi-University Research Initiative, Murray Center at UT, and his expertise is those optical device and integrations and measurements, right? So one device, like among all this, right? So a device that people usually use, right, for optical computing is this so-called micro, ring resonators, right? So essentially, your light comes in, you have a ring, right? Some kind of computation can either pass, not pass, or you can do some kind of matrix. This multiplication operations, right? But usually in the past, one ring has only one controller. However, if we can kind of divide this ring into multiple controllers, so essentially then one device can do kind of dot product and this round trip phase operation. Again, don't worry about the details, but basically if you have K segments, and then you can do a lot of cool computations by going through one ring. And by doing all this, and together with the software training and the pruning and the sharing and all these things, right? Then we found that, we can actually use a significant less number of devices, but meanwhile with a lot of like a saving, in terms of the, number of devices and the number of parameters you need to train and with better noise robustness. Again, I won't go into details, but this is something, again, right, which course hardware, software kind of co-design, try to understand, device, architecture and software. Right? Another thing I like to mention is that previously, we just talked about, hey, you will build a chip, and once you build a chip, right? So, a lot of this chip may be an inference. It's just a one-time deal, right? But sometimes you do want to have a chip which can allow you to do the training. But when you are doing the training, that means you have to tune those weights. That means you are going to consume a lot of power. So then again, right? How do we do the training? And one thing you can, it's kind of hard for you to do is that while you are doing training, you need the forward propagation and then backward propagation, right? But when you do backward propagation, how do you compute those kind of gradients, right? So it's non-trivial. So that's why we use something called the zeros order, stochastic zeros order optimization. Again, I won't go into details, but basically, we can still make it trainable. And one thing, which is nice with on-chip training is that when you are doing on-chip training with like software training, when you are doing on-chip training, you are training using real device, not even measurement, right? It's the real device physics, at that real time to do the, because we are doing, analog computing, right? So that means if you have any of these kind of variations, you naturally, kind of take advantage, you naturally actually can handle those variations very naturally. And that's why, think about previously, as our result shows, right? Previously, if you are doing this kind of, software training, when you map it to hardware, you are going to lose a lot of accuracy. Like, for example, 6% accuracy point drop, right? However, if you are doing hardware training, you are not going to lose any, accuracy, right? So another thing that we have been doing, this is published in AAAI this year, is, let me just quickly show you basically the top idea, right? The top idea is basically, right, previously, when we are doing this paper, right? By the way, yeah, this actually got best paper nomination and some, also from NSF workshop best poster award, right? So, but at that time, right, we are kind of assume all the device is trainable, right? But the problem is that if you allow each device to be trainable and the training, while you are tuning those devices, it actually consumes a lot of, most power, right? So the key idea here is like, okay, we are going to only allow a subset, a significant subset, we are going to fix those, configurations. Do not allow it to change. Only allow a subset to train. And again, I won't go into details, but with this, we found that, we can actually significantly reduce power because, 90 or 90%, we actually, you still need those devices with a fixed weight, right? But you only allow 5% of other device with trainable weights, stuff like that, right? So then you can significantly reduce power. And also that means we can actually even train bigger, networks, right? So yet another new work that actually, I think my student Jiaqi is presenting at NeurIPS, either happening now or next week, right? So basically, remember previously we are using zeros order, and this work actually we are using first order gradient, which allows you to actually scale to even much bigger scale. And again, I won't go into details, but the basic idea is like once you have those devices, right, you can do a forward plus backward. When you're doing gradient computation, right? Usually when you are doing kind of gradient computation, you have to do some kind of dot product of this. But anyway, you can have light comes from this direction to compute the dot product of this, and then the other one goes from backward and compute some dot product of this, and then you compute this. Then you can kind of compute their you can compute actually their in situ first order gradient. And again, I won't go into details, but it's kind of pretty nice way to do it. And so by doing this, basically, right, we found that you can have thousands of times better scalability, and also with very good accuracy, and so on and so forth. Right? All right, so let me conclude. In this talk, I have shown you some sample and case studies and how we can do better placement or some kind of litho gain, and magical with no human in the loop. Essentially, how we can leverage AI, hardware, and software for IC designs, right? But meanwhile, I also showed you, how we can kind of, develop an ultra fast, which light speed, right, and very efficient optical neural accelerators to speed up your core AI computation, right? And I think hardware and software co-design is the key. And my student Jiaqi has done a lot of work on different aspects for scalability, robustness, and because of time limit, right, I didn't have time to show this, right? And then also all kinds of scalability issues. And so I think to conclude, right, I think basically we do need to close the virtuous cycles between AI for IC, and IC for AI, which basically have this software and hardware kind of, remember I showed you this exponential and exponential, right? Whether they can work exponential, show two exponential or whatever, right? I think there's definitely a tremendous potential to leverage each other. All right, with that, I'd like to also thank all my funding agencies and my many students and postdocs who do the real work and my collaborators. So thanks, and I'll be more than happy to take any questions.
Thanks, David. There were about 5 or 6 talks worth of content in that one talk.
Right. I know, right. But this is a general audience, so that's why I try to kind of a little bit more general, so that.
Yeah, you packed it in. Any questions for David? Feel free to type in the chat or unmute yourself. I mean, I have a question. How much, in just regular implementation of, say, deep neural networks, there's a lot of hand and fine tuning, especially of the hyperparameters that goes into achieving state of the art. I mean, how much sort of fine tuning do you have to do with these methods? Do you find that, you sort of typically something kind of works and you can fine tune later, or do you really have to fine tune a lot in order to make progress?
I think we didn't do a lot of very heavy duty hand tuning, right? Because a lot of in the machine learning community, there are a lot of very good, architecture and some open source things people have already done, right? So while we, apply it in our framework, right, maybe we do a little bit. I need to check with my students. I don't know if any of my students are here, right? I guess they are busy for the deck deadlines. So, but anyway, I don't think we have done a lot of hyperparameters. You do need a little bit, I guess, but not very heavy duty, right?
And is there a particular problem where you feel like machine learning methods should have worked, but they didn't work, and it's sort of mysterious as to why they didn't work? Or
so you are talking about some EDA design automation for chip design? Yeah, usually, of course, chip design, there are also a lot of systematic approach people have already done before, right? For example, when people are, depends on, right? So as you can see, right, when we are doing this to help chip design, one is to really leverage the hardcore kind of, machine learning hardware and software, right? Like Dream Place. So that, people have already, it's a 50-year plus of research, and people squeezed every bit of juice pretty much there. Of course, if someone really magically come up with a really new formulation and wow, get another like 10%, that's tremendous, right? I think ultimately you probably need also, need some more like a real kind of data training approach together with this analytical approach, maybe, right? So with some reinforcement learning, ultimately you need kind of, how do I say, try and error to see different kind of combination methods work, right? So of course, if you just use deep learning, there's a lot of explainability issues there, right? So sometimes you just know, wow, it kind of works. You don't know exactly why, right? So yeah.
But it's interesting that the architectures that were developed, in the deep learning community, it seems like kind of translate naturally over to the problems that you're working on.
Yeah. I think, for example, the image, like the GAN, right, that actually translated pretty well, right, for for the our litho game, right?
Right.
Of course, we need to tweak it a little bit, right? So, yeah.
Okay, well, if there are no other questions for David, thanks again for being here. You know, it's an incredibly busy and exciting area, so we appreciate the overview. And thanks to everyone else for stopping by. Please check the ifml.institute. We'll be back with seminars in the upcoming weeks. So thanks again, everyone.